Test, 1, 2, 3. Test, 1, 2, 3. Okay, so let's get started. I know I might be a minute or two early. I do not have TAs today, and therefore I cannot monitor the chat room. Usually I have the TAs monitoring the chat room because when I'm in presentation mode, the screen I have only shows the presentation. I can't see any of the Zoom chat or anything else. I have to stop share in order to see chat. So as reluctant as I am to do this, if you have a question today, you're going to have to unmute yourself and butt in and just ask your question so I can respond. If a TA happens to show up, then we'll obviate this problem and you can still use the chat room. But for today, let's just use your microphones. Are there any questions from last time? Not a one. Good. You probably noticed I did not post any homework for you. I'd like you to believe that it's because I'm a kind soul, but the reality is I just didn't have time to make them up and post them for you. So expect something today or tomorrow. There might be 2 problems per lecture through the end of the semester. That's what you should plan for, at least. Today, we're going to continue with what we were doing in the past. And what that is looking at the energy problem and now talking about energy losses. So we'll start off with a brief review. Recall what we're using to describe energy losses is that the frictional resistance loss is described by the Darcy-Weisbach friction equation. That equation is a friction factor F times the distance between 2 points in your analysis divided by the pipe diameter times the velocity head. So for example, we could have a piping system that looks something like this. And you're looking at a profile, so there are difference in elevations. And we're using the energy analysis. And that means you have to be able to draw a path line between 2 points in an analysis. If you cannot draw that path line, you cannot do the energy analysis. So for example, if this is one single pipeline, and let's make it look like a pipe. So we have flow going from left to right here. And in this case, hold on, the TA just showed up. Sorry, TAs needed to be let in. So in this case, now that we have this pipeline, we could, for example, select 2 points, 1 and 2. And for these 2 points, again, if we're doing an energy analysis, we may have a datum where the elevation is 0. And we would say that the energy at 1, B1, and the energy at 2 can be equated in the energy analysis, only now B1 is not equal to B2, but we have some energy losses. What that means is that there's some slope to the energy grade line. And the difference in energy between point 1 and point 2 is that friction loss. That friction loss is described by the Darcy-Weisbach equation. And again, there are other equations. I'll talk about one other one once we get through this section. So in the Darcy-Weisbach equation, again, H sub F is energy loss due to friction, and it has the dimensions of length. The Darcy-Weisbach friction factor is dimensionless. L is the pipe length, E is the pipe diameter, and V is the velocity, G is gravity. So how we find the Darcy-Weisbach friction factor is what's called the Moody diagram. And again, the Moody diagram can be described by equations. So you had a handout with this Moody diagram. And on the other side of the handout were all the equations that describe different parts of the diagram. Most of those equations and the Moody diagram are in your textbook. Remember, there are basically 4 axes on this plot. One is the friction factor on the left-hand side. The lower horizontal axis is Reynolds number. And then the blue contours are what we call the relative roughness, the absolute roughness size, K sub S, divided by the pipe diameter. And on the top, there are diagonal black lines, and we'll be talking about those today. And they are contours of constant values of RE times F to the 1/2. Remember, RE is the Reynolds number, it's dimensionless. K sub S over D, relative roughness, dimensionless. REF to the 1/2, F and RE are dimensionless, so REF to the 1/2 are dimensionless. So that's the beauty of this diagram, everything's dimensionless on it. If you know any 2 of these 4 coordinates, you know the other 2 automatically. Because once you plot a point on this diagram, the other 2 points are all known. And remember, the vertical left axis are vertical lines, and there are also other axes that are vertical. They are describing each vertical line as a Reynolds number of a different value. Each horizontal line is a different value of the friction factor. The curved blue lines are basically can be viewed as axes, but again, they're curved. And then lastly, REF to the 1/2 are sloping lines of constant values of RE times F to the 1/2. So again, the next page of that handout that had the Moody diagram on it had all these different equations. And again, there's only one equation for the laminar zone. There are different equations for the smooth pipe, which is a very specific curve on the diagram. It's always a transitional boundary layer. And then there are other equations for when you're anywhere in the transition zone, and we've got one equation explicitly for turbulent, but again, you can use any of these three transition equations because ultimately they form a plain horizontal line out once you get out to the transition. So in the laminar zone, friction factor is only a function of Reynolds number. In the turbulent zone, friction factor is only a factor of relative roughness. E over D or K sub S over D are relative roughness. And in the transition zone, whenever you're in transition, anywhere in that zone, the friction factor is both a function of relative roughness and Reynolds number. When you're on the transition zone in the smooth pipe curve, basically smooth pipe means the relative roughness is 0. Okay, and then other things we're going to want to pay attention to, and we'll do these in examples today. Whenever you use one of these equations, you have to make sure that you subscribe to the ranges of validity. Otherwise, the answer you get is bogus. So that's more or less review. And again, from that previous page of all the equations, there's one equation for the laminar zone, multiple equations for the transition zone, two equations I'll typically use for turbulence, Swami and Jane and von Karman. And then again, oops, the smooth pipe curve is this lowest curve. And that's where you had three equations just for that one curve. And again, that the Moody diagram has three zones: laminar, transition, and turbulent. And the smooth pipe curve never escapes the transition zone. Okay, so this is the last slide of review. There were three fundamental types of closed conduit problems: the problem in which we're calculating the energy loss, the problem in which we're computing discharge, and problems where we're computing the pipe size, the pipe sizing problem where we're calculating the diameter. And again, these all work off of an energy balance. And so in the pipe, we have an energy balance from, say, 0.1 to 0.2. And B1 is the total energy for 0.1. B2 is the total energy for 0.2. And the difference between those two energy grade lines is a head loss term. If the head loss is only due to friction, so head loss can be friction or minor losses. We've discussed this before. Minor losses are transitions like entrances, exits, T's, Y fittings, valves, gates, etc. If we're going to be talking about those next. So right now we're focusing just on friction loss and the Darcy-Weisbach equation describing that friction loss. And so when we set up the energy analysis or the energy balance between 0.1 and 0.2, the difference between those two, again, is the friction loss. And within this one equation are the three types of problems: calculate H sub F, calculate the discharge, which in essence is saying calculate the velocity, or calculate the pipe size, the diameter. So last class, a week ago today, we looked at the energy loss problem. And this was the solution methodology we looked. If you recall, we had a pipeline carrying carbon tetrachloride, and we set up an energy balance equation to calculate ultimately the pressure drop in a certain length of pipe. And this was the strategy we used. But again, all of these classes of problems start with an energy balance. So we want to move on today to the discharge problem, and we'll probably continue with this next time. So fundamentally, for the discharge problem, we do not know the discharge and therefore velocity. Remember, these two are evaluated when we use the continuity equation. Discharge is velocity times area. Velocity appears in the energy equation as the velocity head. It appears in the Darcy-Weisbach equation, again, as the velocity head. But remember, embedded in the friction factor, we need to know, for example, the Reynolds number in order to find the friction factor in order to find the velocity. And so the velocity is also buried in the Reynolds number. So this makes the solution challenging because we have more variables than equations. For example, we can't find the friction factor until we know the velocity, and we don't know the discharge, so we don't know the velocity. So when you have more variables than equations, you either need another equation, you need a boundary condition, or it's a trial and error solution. And today we're going to look at this method, finding another equation in order to come up with a solution. And I'll show you 3 ways of doing that today. And if we have time, we'll get into this last one, trial and error. So another equation. And this is really important for all the methods we're talking about today. All of the energy losses are just friction losses. There are no minor losses. When that's true, one thing we can do is combine the Darcy-Weisbach equation, dW, Darcy-Weisbach equation, with the fundamental equation describing the Reynolds number. So for example, we could solve both equations for velocity, or solve the Reynolds number equation for velocity, and then substitute that into the Darcy-Weisbach equation. So for example, V is equal to nu RE over D. And we could put that substitution here and then just solve the equation. Or solve this equation also for V and then make the 2 equal to each other. So we're combining these 2 equations, and lo and behold, when you combine those 2 equations, one thing you can isolate is this term Reynolds number times friction factor to the 1/2 power, which, remember, that's the upper horizontal axis on the Moody diagram. And on the right-hand side are, this is not F, that should be H sub F. And the equation is on the top of the Moody diagram. So I just caught that error. So on the right-hand side are all variables you will know in this class of problems, as you will see. And again, we don't know the discharge, but we do know other information. So in this class of problems, what you do is calculate the right-hand side. And by calculating the right-hand side, you get one of the 4 coordinates needed for the Moody diagram. We just need one other coordinate. And that other coordinate is the relative roughness. So in this class of problems where we're trying to calculate the discharge, one way to solve it is to calculate Reynolds number times friction factor to the 1/2, calculate relative roughness, and with those 2, we can find the friction factor. And once we have the friction factor, we can compute the Reynolds number. And once we have the Reynolds number, we can compute the discharge and velocity. So again, what I'm showing you is the solution strategy. I'm going to show this exact solution strategy in the next example, and we're going to follow this strategy. So let me give you the problem for example 1. Again, what we're doing in this class of finding the discharge, we're going to calculate a value for REF to the 1/2. That will give us a contour to follow. We will calculate a value of relative roughness. That will give us a relative roughness contour to follow. Where those 2 intersect, you go horizontally over and read the friction factor. Once you have the friction factor, you can then calculate the discharge, as you will see. So this is fundamentally what we're doing. So for example 1, we're going to have a pipe. And in this pipe, what we know is we're going to have a friction head loss of 8 meters. So this is H sub F in a length of 5 kilometers of pipe. You're given the relative, the absolute roughness, 0.405 meters is K sub S, and the pipe diameter is 0.5 meters. What we don't know in this problem is calculate the discharge. You may think this is an obscure or an academic problem, but one of my first years here at UNH, the city of Manchester had this information and they wanted to know how much water was in the pipe. So think of it. You've got a pipe that's a ½ meter in size. Do you know how expensive it is to put a gauge, a metering gauge in that pipe? That would cost a few $100,000. What would be much cheaper? Measuring the pressure at 2 different locations, just like you did in Fluids Lab. And then you can estimate the discharge. It's a lot cheaper. So this is actually a real problem, and distribution networks and other pressure piping systems will use pressure drop, just like you did in lab, to estimate discharge. So we know that the fluid flowing is water, and therefore we know what the kinematic viscosity is, which will be used, of course, in the Reynolds number. So we don't know the discharge. This, again, that's wrong. That's what now I'm just copying and pasting. So in this case, we're going to calculate the Reynolds number times the friction factor to the 1/2 power. We got that equation, this equation you see, by combining the Reynolds number with the Darcy-Weisbach friction factor equation. So you can see diameter to the 3/2 power divided by the kinematic viscosity times 2 times the acceleration due to gravity times the friction loss of 8 meters divided by the pipe length of 5,000 meters, all to the 1/2 power. You have to remember, Reynolds number is dimensionless. Friction factor, when I put a 0 over the top of it, dimensionless. That means that everything on the right-hand side of this equation, which individually each component does have a dimension, they need to be combined in such a format that the right-hand side is in fact dimensionless. So for example, if you had used the diameter in centimeters, you would not have a dimensionless number on the right-hand side. You needed to convert that centimeter dimension to meters. So we go all through that, and to 3-place accuracy, you get REF to the 1/2 of 48,200. That's one of the 4 axes on the Moody diagram. The other thing you were given were the pipe diameter and the relative roughness. So we can calculate the relative roughness. Relative roughness is absolute roughness, K sub S of 0.405 meters, divided by the pipe diameter, 0.5 meters, and that gives us 0.301 or 10 to the minus 4, dimensionless. So now we have 2 coordinates in which we can enter that Moody diagram. So from the top, we know that REF to the 1/2 is 48,200. From the right, and you can see I drew that contour, and obviously it doesn't have a value right on one of the black lines. And so you're visually looking in between the two, using the computer graphics, I can make it look parallel, but when you're just using your eyeballs, you're just trying to bring that line down parallel between any of the other 2 black contours. The relative roughness, we calculated to be 0.301, and you can see 0.301 on the right vertical axis. And remember, that is a contour that is curved. And so you just keep following that contour. You stay on the 0.301 relative roughness contour until it intersects the REF to the 1/2 contour. And where those 2 intersect, you will first notice that it's in the transition zone. Remember, the transition zone is bounded by that sloping dashed line and the laminar zone. So one, you notice this is in the transition zone. Once we have the coordinates where REF to the 1/2 and K sub S over D intersect, we go horizontally over. And again, I expect you to be able to read 3-place accuracy off this diagram if you use the diagram. And so I read off of this diagram 0.0152 for your friction factor. And again, if you have questions, the TAs are here, so feel free to chat, use the chat box, and hopefully they'll confuse you better than I do. So friction factor of 0.0152, that's what we just found. We also found that Reynolds number times friction factor to the 1/2 is 48,200. So of course, The Reynolds number is REF to the 1/2 divided by F to the 1/2. So that's 48,200 divided by 0.0152 to the 1/2 power, which gives you about 391,000. I just want to back up to the previous slide. You could have just gone vertically downward. And you can see that it's pretty close to 400,000. I doubt you could have read the accuracy of 391,000, but that's a good visual check for you. So once you have the Reynolds number, you know that's equal to velocity times diameter over nu. Or remember, V velocity is Q over A, which is the discharge over pi over 4 times the diameter squared. And if you substitute that into the expression for velocity, you get this second term. So the second term, you can rearrange and solve for discharge directly. But what I'm first going to do is rearrange the Reynolds number to solve for velocity. So the Reynolds number times the kinematic viscosity divided by the diameter is the velocity. And that gives us a velocity of 1.02 meters per second. And then using continuity, discharge is equal to velocity times area. The velocity is 1.02 meters per second, pi over 4d squared gives us a discharge of 0.20 cubic meters per second. And again, that's what we were after. We were after the discharge. So that's one way of solving the discharge problem. I'm going to do this exact same problem 2 other ways. The other way to do this problem, instead of using REF to the 1/2, is to combine the Darcy-Weisbach equation with one of the empirical equations. So remember, on the last handout that had the Moody diagram and all the equations describing pieces of the Moody diagram, if you combine the Darcy-Weisbach equation with any one of those empirical equations, you can tease out velocity or discharge. On today's handout, I packaged some of those combinations. Those equations are also in your textbook. So these are the equations from the previous handout, and you saw these earlier today. So for example, if you're in the transition zone, remember, we just did this problem. We know we're in the transition zone. If you hadn't already done this problem, you do not know you're in the transition zone. So if you selected one of the combinations that I'll show you on today's handout, the next thing you have to do after you get an answer is make sure you check the range of validity. If you don't do that, I would never consider your answer correct. So for the first combination, we're going to take the Darcy-Weisbach equation and combine it with Colebrook's transition equation. So the Darcy-Weisbach equation looks like this. From the very last slide, the Reynolds number looks like this. And again, from the very last slide, the Colebrook equation looks like this. And this is from the handout from last class. And what you get when you do that combination is the first equation on today's handout. And again, by combining these 3 equations, what you have is the discharge is equal to, if you look at the right-hand side, we know the pipe diameter, acceleration due to gravity we know, diameter we know, friction loss we know, pipe length we know, relative roughness we know, kinematic viscosity we know everything on the right-hand side. So that's the beauty of these equations. Caveat, first one, all losses have to be friction losses. You cannot use these equations if a part of the total energy losses between your 2 energy analysis points is not friction losses. Just keep that in mind. And then the other caveat is you have to meet the requirements of the equations. So, same problem as before. We've got a pipe. And in 5 kilometers of this pipe, we have 8 meters of frictional resistance losses. It's got an absolute roughness of 0.405 meters. It's got a pipe diameter of 0.5 meters. We don't know what the discharge is, and we know water is flowing, and we know the kinematic viscosity of water. This is the equation, again, first one on your handout, and it was appearing on the previous slide. What we have to do is substitute in the diameter, the absolute roughness, kinematic viscosity, pipe length, and friction loss. All of those go into this equation, and you get 0.22 cubic meters per second, which is about a 10% different than the last answer. Before it was 0.20. And again, when we get more than 5% differences, that kind of should make you raise an eyebrow. So we got an answer. However, just above that equation are the caveats. When you combine Colebrook equation with the Darcy-Weisbach equation, you need to have your Reynolds number in a certain range. Either the absolute roughness needs to be greater than the laminar sublayer thickness, or K sub S U star over nu is in a certain range. And I'll explain what that is. So we had a discharge of 0.22 cubic meters per second. That's what we just found. From that, we rearrange continuity to calculate the velocity, 1.12 meters per second. From that, we can calculate the Reynolds number. And that Reynolds number is 4.31 times 10 to the 5th, and we need it to be between 4 times 10 to the 3 and 10 to the 8th. We certainly meet that range. That's okay. The other requirement was this curious term K star, KS times U star over nu. So U star is known as the shear velocity. It's not a real velocity. It's a construct from shear stress. It has the units or the dimensions of velocity, meters per second, foot per second, length per time. So the shear velocity, U star, is equal to the shear stress at the pipe wall divided by the density, square root. So the dimensions of tau 0 over rho to the 1/2 power are the dimensions of length per time. If we substitute in what we know for tau 0 is equal to the acceleration due to gravity times something called the hydraulic radius. And we'll be talking about that a little bit later. This is actually something we will use to help us analyze non-circular cross sections. The hydraulic radius is equal to the cross-sectional area over what's called the wetted perimeter. So if we look at the cross-section of a circular pipe, for a circular pipe, the area is pi over 4 d squared. Hopefully there's no problems with that. The wetted perimeter is the surface area between the solid boundary and the fluid. For a circular pipe, the wetted perimeter, we're going to call P, is just the circumference, and the circumference is pi d. So if you take the area over the wetted perimeter, pi over 4 d squared over pi d, you get d over 4. That is true for a circular pipe. And we're going to use this again, this construct for non-circular cross sections. So again, the hydraulic radius, RH, is area over wetted perimeter, and that's equal to d over 4. And that's what you see in the latter part of the equation. And then S sub F is known as the friction slope. Friction slope. It's the slope of the energy grade line. That's what it is. And so it's equal to the friction loss, H sub F, divided by the distance over which it occurs. Remember, the friction loss in this problem is 8 meters, and the length of the pipe is 5,000 meters, 5 kilometers. Diameter of the pipe, 0.5 meters. Acceleration due to gravity, 9.81 meter per second squared. So when we calculate the shear velocity, we get, again, something with the dimensions of velocity. And all you can say is the shear velocity is 0.044 meters per second. Typically, we use shear velocity, for example, in streams and rivers when we're trying to estimate sediment transport or stable particle size. So that's a common usage of shear velocity. So why we calculated that was, again, up above, you see this caveat that the absolute roughness, K sub S, times the shear velocity divided by kinematic viscosity has to be within a range of 5 to 70. When we calculate it, we get a value of 1.7. That is not within the range. And so this answer should not be considered valid. Consider it a guesstimate because you're out of range to use this equation. Got it? That's really important. If you use one of these equations on homework or an exam, I expect you to do the checks. If you don't do the checks, I guarantee you will lose points, even if you get the right answer, because getting to the right answer means showing all of your work. And on the instructions to the exam, I'm always very clear, show all of your work. We need to see how you arrived at your answer. Just saying you copied it from someone else is not good enough. So what we did was combine Colebrook with the Darcy-Weisbach equation. The second equation on today's handout combines the Darcy-Weisbach equation with the Swamy and Jain equation. So again, we're taking the Darcy-Weisbach friction loss equation, the definition of the Reynolds number, and we're taking the transition Swamy and Jain equation, which looks like this. This is from the handout from last time. It is also in your book. So when you combine all of those, you get the second equation on today's handout. And that equation looks like this. And again, everything on the right-hand side is a known parameter in the class of problems we call the discharge problem. How do you know it's a discharge problem? You don't know velocity or discharge. For example, the example we're doing today, it's quite clearly says, what is the discharge? Find Q. So in this problem, again, we know the relative roughness. It's the same problem. We're going to use the combination of Swamy and Jain and Darcy-Weisbach. So when we plug in everything we know into this equation, we get 0.202 cubic meters per second. So remember, backing up, the first way we looked at this was to calculate Reynolds number times friction factor to the 1/2. And when we did that method, we got 0.2 cubic meters per second. But we were reliant on reading off of that Moody diagram. And I agree, it's hard to do that with a lot of accuracy because you have log scales. But we got 0.2 cubic meters per second. The second way we looked at this was to combine the Colebrook equation with the Darcy-Weisbach equation, and we got a discharge of 0.22 cubic meters per second, but we found that we were out of specifications for that equation. We were in specification in the first method, REF to the 1/2. The second method was not really usable because we were out of the validation criteria range. So with this discharge, we get a velocity and we get a Reynolds number. And these answers are very similar to the first method we used. So from your handout from today, you can see that there is a criteria range for the relative roughness, and there's a criteria range for the Reynolds number. So we're just going to check those now. Oops. So the Reynolds number is about 4 times 10 to the 5th. That's certainly within range. And the relative roughness is 10 to the -4, which is also in range. So basically you meet all of the qualifying criteria to use this equation. So the answers from part 1, where we used REF to the 1/2, or part 2 are both acceptable. That answer in the middle, the second method we tried, isn't. So what I'm going to do for the remainder of today is set up this method. I don't think we'll have time to go through an example, and then we'll do an example with this method next time. That's where we'll start. So again, when all else fails, if you don't like those two methods, but remember, you could be using those methods if you are not in the transition zone. You can't use the Colebrook and Darcy-Weisbach or the Swami and Jain Darcy-Weisbach because those are equations for the transition zone. If you're in the laminar zone, it's a no-brainer because you already know everything is defined. Reynolds number, sorry, friction factor is 64 over the Reynolds number. You can combine the Reynolds number with the Darcy-Weisbach equation, and the equations are in your textbook. You get a direct solution. So it's not trial and error, and the only two combinations you're making when you're in the laminar zone is the Reynolds number combined with Darcy-Weisbach equation, and you get a direct solution for friction factor. When you're in the turbulent zone, you would need to combine one of the turbulent equations, von Karman, for example, or possibly Swami and Jain. If you're out of specification with that, or if you're out of specification when you're in the transition zone, you're thrown into this trial and error method. So that's why I think it's important to go through this for you. So you're setting up a solution methodology. And as the name implies in trial and error, you're guessing something. And I'll give you a guidance on what to guess. And after you guess something, you're going to go through this whole solution trajectory and recalculate it. And what you want is for your guess and the calculated value to be the same within a tolerance. If they're not, you have to re-guess. So you can either set up a strategy based on discharge, or you can set up a strategy based on friction factor. Personally, I think it's a little easier if you guess at friction factor. Some other people, you may not have a physical feel for friction factor versus discharge, and so you can certainly do this with discharge. The working equations, no matter which way you do this, whether you're guessing discharge or friction factor, continuity, energy, Darcy-Weisbach friction factor, Reynolds number, relative roughness. No matter which method you do, this is what the equations you have to use. So, and again, we're still in the discharge class of problems. So I'm going to show you a strategy for friction factor. First thing you do is set up an energy balance for 2 points, not 2 points, pints. I guess I was doing this last night. Setting up energy balance for 2 points in a system in terms of velocity. So for example, we've got our pipe, just like the previous problems. And between 2 points, 1 and 2, we've got the energy grade line decreasing in the direction of flow. And we would say that B1 is equal to B2 plus H sub F. And you know, when I write B1, that's V squared over 2G plus P1 over gamma plus C1. So by setting up that energy balance, what comes out of that is velocity as some function of friction factor. That's what's going to come out of it. And again, I'm just giving you the methods. I'm going to go through a numerical example next class. And the other thing you know is if you did know the velocity, you could calculate the Reynolds number because you know the pipe diameter in this class of problems and you know the kinematic viscosity of the fluid. So these are just two functions. For example, V is equal to 7.2 over the square root of F. That is velocity as some function of F, right? That's all it is. And something like that would come out of an energy balance. I'm telling you that. And again, next time we're actually going to come up with this. That 7.2 is just a number I picked out of the air. Depending on the problem, it's going to be different. And then again, Reynolds number is velocity times diameter over kinematic velocity, viscosity. So what we would do is, that's interesting. I just found new buttons on this pen that I've never touched before. And all of a sudden they did something. All right, so the next thing we would run into is the second step after we've done our energy balance in step 1 is to calculate the relative roughness. And again, think of the problem we just did 3 times. You were given the absolute roughness, you were given the pipe diameter. Now, at this point, you're going to assume the friction factor. And we're going to call that FA, A for assumed, the assumed friction factor. What is a good range? For most pipe, 0.015 to 0.02 is a good guess. If it's brand new, really smooth, like plastic pipe, you could go as low as 0.012. If it's very old, corroded pipe, it could be as high as 0.05. Okay, so if you don't know, I would say start. And what happens is this actually, through trial and error, should only take 2 or 3 trials and error. It converges very quickly, as you will see, even if you guess it really poorly at the start. Once you have a friction factor, from step 1, you can now calculate the velocity. The only thing that prevented you from calculating the velocity in step 1 was the friction factor. You didn't know it, but now you just guessed it. So now you can compute the velocity, which means you can compute the Reynolds number. With the Reynolds number and the relative roughness, you can either go to the Moody diagram or use one of the equations and find the friction factor. And here we're going to call it FC, the computed friction factor. It's highly likely FA and FC are not the same on your first guess. We want it that way, but it's probably not. So what you will do next is calculate a difference, or what we'll look at the difference between those two, and we'll compare that to a tolerance. So if the absolute value of the assumed friction factor minus the computed friction factor is less than 0.405, you're done. Remember, once we assumed the friction factor, the velocity was a function of the friction factor. And since we met our tolerance, if the absolute value of assumed friction factor minus computed friction factor is less than this tolerance, within these calculations, we have the velocity, and therefore with continuity, we can calculate the discharge. It's more than likely that you're out of tolerance, and that means that the assumed friction factor minus the computed friction factor is greater than or equal to 0.405. And that means you need to make a second guess. Your next best guess is what you just computed for the friction factor. So for example, let's say you assumed a friction factor of 0.015. You computed a friction factor of 0.017. That means that absolute value of FA minus FC is equal to 0.015 minus 0.017, which is 0.002. And that is greater than 0.12345. And so second trial, make that last guess your next guess, your last computed value, your next guess. So this is first trial. Okay. And so this looks kind of complicated. And again, probably just because you've never done this before. However, once you go through it, it's really not so bad. So let's I'm just adding some more slides to this presentation so I can continue. since I have 5 minutes remaining. Oops, I gotta share again. Technology. So if we were doing the same problem, trial and error. And remember, in that problem, we've got a length of pipe equal to 5 kilometers. We've got a pipe diameter equal to 0.5 meters. We've got an absolute roughness of 0.12345 meters. And we had water flowing. And we had a friction loss of 8 meters in that 5,000 meters. So that's the same problem as before. And what we would say from our energy balance, H sub F is F L over D, V squared over 2J. And from that equation, again, the first step, from the energy equation, we want to get velocity as a function of friction factor. That's this equation. So I'm just going to rearrange this equation to solve for velocity. So velocity is going to equal 2g diameter H sub F divided by friction factor times L. That's how we rearrange that equation. And again, in that equation, G is 9.81 meters per second squared. Diameter 0.5 meters. Friction loss 8 meters. L is 5,000 meters. And so this gives us an equation where F is equal to 0.125 over the square root of F. That's some function of friction factor. If we knew F, and that's what we're going to do, we're going to assume F, then we know the velocity. Similarly, the second step is Reynolds number is velocity times diameter over nu. And again, at this point, you don't know velocity. So this is velocity times 0.5 meters over 1.3 times 10 to the minus 6 meters squared per second. And that just tells us that the Reynolds number is 3.85 times 10 to the 5th. V. This is J prime of V that I showed you in the steps before. The third thing was to calculate relative roughness, which we've already done 3 other times today. 0.405 meter over a diameter of 0.5 meter is 10 to the minus 4. 0.0001. Okay. So first step, let F equal 0.02. Remember, I suggested 0.015 to 0.02. It's a reasonable number. This is our assumed friction factor. And therefore the velocity, 0.125 over square root of 0.02. And that gives us, and we've been maintaining consistent dimensions, 0.886 meters per second. Remember, we've already done this problem 3 times. We should have had a friction factor of 0.0152. So I know 0.02 is wrong. You should know 0.02 is wrong. We can calculate the Reynolds number then. And the Reynolds number is equal to 3.41 times 10 to the 5th. Again, we just use the equation up above to calculate it. And with that Reynolds number, And that value of K sub S over D, if I use the Swami and Jain equation, I would get FC is equal to 0.0152. Again, I used this Reynolds number and this relative roughness in the Swami and Jain equation. And that gave me a computed friction factor. And now I need to look at the difference, FA minus FC, 0.02 minus 0.0152. And that difference is equal to 0.0048. And that is greater than 0.405. That's not any good. So second trial, what we're going to do is let FA now equals 0.0152. And if you go through this, as we found before, I know I'm at the end of class, so I'm just going to leave you with that parting thought. If you go through this, you would see that this would converge on your answer. Okay. And again, you would find that you achieved about the same discharge we found when we combined the Swami and Jain equation with the Darcy-Weisbach equation, a discharge of 0.202 cubic meters per second. So the trial and error solution isn't that bad once you set it up. Quite honestly, once you have the equation set up and you program them into a spreadsheet, it might take you a few minutes to program them, but then it takes you seconds to just go through it. Question?
One of the students asked, will you ask the student to use a specific method to solve these problems, or can they choose to use any of the methods you showed today?
Yeah, so when it's up to you on an exam or your homework, I leave it up to you. When you leave here, I leave it up to you. I'm not going to dictate any one method. I will tell you that what I see most people using nowadays is the Swami and Jain equation when you're in the transition zone, and any derivatives from using that equation. That's what I see most commonly in practice and in the classroom. Okay. All right. If there's no other questions, then I know I ran a little over today. I'm just giving you your money's worth, but I will stop sharing and give you a second to either write questions or end. I will be ending it now.